Imagine you are trying to predict where a falling leaf will land. The old way, using tools like ARIMA or LSTM, is like calculating the wind speed and gravity equations from scratch every single time. It is hard work. Now, imagine a new way. You ask an observer who has watched 1 billion leaves fall. That is what we call a foundation model. In this paper, we are checking if this experienced observer, specifically a large language model, repurposed, can beat the calculators at predicting water tank levels. We want to see if patterns in language can translate to patterns in numbers without us having to teach the model the rules of physics first. Look at this setup in Figure 1. It is a race on 2 different tracks. On the top track, we have the heavy lifters, TCNs and LSTMs. These are the traditional neural networks that crunch numbers the hard way, training for epochs to learn the specific dataset. On the bottom track, we have the talkers, Gemini and OpenAI. We treat them differently. We don't train them. We just feed them a window of data like it is a sentence in a conversation and ask, what comes next? We test them with 0 shot, no examples, and few shot, a couple of examples. We want to see if the model that just reads the data can outperform the model that studied it. To understand the players, you have to look at their brains. Times FM is a transformer, similar to the tech behind ChatGPT, but it reads numbers like words. It has read 100 billion data points. It knows the grammar of time passing. Then we have TCNs, temporal convolutional networks. They look at history through filters, expanding their view like a camera lens, zooming out to see the past. We are testing in-context learning here. It is like showing a chef a finished dish and saying, cook this, without giving them a recipe. The model has to figure out the pattern instantly, right there in the moment, without any practice or parameter updates. To make this a fair fight, we need a standard test. We took the SWOT data set, which records things like valves opening and tanks filling in a water treatment plant. We cut this continuous movie into 720 frame clips. We show the model a clip and say, predict the next frame. For the language models, we literally turn the numbers into text. We say, here is a list of numbers, 2.2, 2.2, 2.2, tell me the next one. It sounds crazy to treat math like a paragraph, but that is exactly what we did. We then measure how wrong they are using root mean squared error, RMSE, to see who gets closest to the truth. Look at the charts in Figure 2. The blue line is what actually happened, the reality. The orange line is the model's guess. Look at Figure 2e, that is times FM. It sticks to the blue line like glue. When the water level jumps, times FM jumps with it. Now, look at the deep learning models in 2F, TCN, and 2G, LSTM. See that gap? They are lagging. They are chasing the bus after it has already left the station. The foundation model, times FM, sees the jump coming because it understands the context of the pattern, whereas the traditional models are struggling to catch up to the volatility. The winner is clear. Among the models compared, times FM crushed it. It had the lowest error and was super fast, only 266 seconds. It is like a master mechanic fixing an engine by ear. The generalist, OpenAI's O4 Mini, was smart and accurate in 0-shot mode, but it was slow. It thought too long, taking over 21,000 seconds. The old-school LSTM, it really struggled. This tells us something huge. You do not always need to train a model from scratch. You can take a pre-trained giant, show it your data, and it just gets it. Though this be madness, yet there is method in it.